behavioral modeling using UML. Now we start the last chapter from this section, architectural modeling using UML. So syllabus for architectural modeling using UML is component, deployment, collaboration, patterns and frameworks, component diagrams, and deployment diagrams. Textbook for this chapter, the Unified Modeling Language User Guide by Grady Booch, James Rambagh, Ivor Jacobson, by Addison Wesley. CO for this chapter is list the object of UML for a given problem statement. So first we start with the point components. So in this chapter we will study the component interfaces and realization, modeling, executable and libraries, modeling tables, files and documents, modeling an API, modeling source code, mapping between logical and physical models. So components live in material world of bits, and therefore there are an important building blocks in modeling the physical aspects of system. A component is a physical and a replaceable part of system that comforts to and provides the realization of set of interfaces. So you use components to model the physical things that may reside on a node, such as executable libraries, tables, files, and documents. A document typically represents the physical packing of otherwise logical elements such as classes, interfaces, and collaborations. Good components define crisp abstractions with well-defined interfaces, making it possible to easily replace older components with newer compatible ones. So, introduction of this chapter with an example. The end product of construction company is physical building that exists in real world. You build logical models to visualize, specify, and document your decisions about the building envelope. The placement of walls, doors, and windows, the routing of electrical and plumbing systems, and overall the architectural styles. These are in the form of components. When you actually construct the building, these walls, doors, windows, and other conceptual things get turned in real physical things. And these logical and physical views are both necessary if you are a disposable building for which cost of scrap and rework is essentially zero. You can probably go straight to the physical building without doing any logical modeling. So, on the other hand, you are building something enduring for which the cost of change or failure is high, then building both logical and physical models is a pragmatic thing to do to manage the risk. Whenever there is a risk, there is a need to logical as well as physical model. So first you should have to construct logical model, and then you can do the physical model. So it's say in the same way The things when building the software intensive system, you do logical modeling to visualize, to specify and document your decisions about vocabulary of your domain and the structural and behavioral ways those things collaborate. You do physical modeling to construct the executable system, whereas these logical things live in the conceptual world. The physical things live in the world of beats. That is, they ultimately reside the physical node and they can execute directly or can, in some indirect manner, participate in an executing system. In the UML, all these physical things are modeled as component. A component is physical thing that conforms to and realizes a set of interfaces. Interfaces, therefore, it is a bridge of logical and physical models. For example, you may specify an interface for a class in logical model, and that same interface will carry over to some physical components that realize it. So this is the example of component. Component can be shown like this, and this component, for example, name is given as kernel32.dll. So this is a graphical representation of component. This canonical notation permits to visualize a component apart from any operating system or programming language. Using stereotypes, one of the UML's extensibility mechanisms, you can tailor these notation to represent specific kinds of components. Component can be shown by this notation, and this is the name of component. So what are the terms and conditions or concepts? Terms and concepts regarding component. A component is a physical and replaceable part of system that conforms to or provides realization of set of interfaces. Components is like a bricks in the for building construction. It works as a brick in building construction. Component is physical and replaceable part of system that conforms to or provides the realization set of interfaces. Graphically, a component is rendered as a rectangle with tab. This is the component rectangle with these two tabs. This is the representation of the component. So every component must have a name that distinguishes it from other components. And a name is in textual string. A name alone is known as simple name. And a path name is component is prefixed by the name of package, which is in which that component lives. See, see, this is the so see these are the examples of simple and this is simple name agent dot java. This is simple name. Then again fraud agent dot dll. This is simple name. These are the attributes of this class or these components. Realizes, fraud agent, fraud policy, pattern search. These are the attributes of these components. And this is the extended components, that is path name, that is system, then scope resolution, then dialog.dll. This is the path name or extended components. So components and classes, in many ways components are like classes. Both have names, both may realize a set of interfaces, both may participate in dependency, generalization, association relationship, both may be nested, both may have instances, both may be participants in interactions. Components are like classes. Classes have the properties, same properties have the components. So classes represents logical abstract, component represent physical things. Classes represent logical abstractions, whereas components represent physical things that live in the world of bits. In short, components may live on nodes, classes may not live. This is the difference between component and classes. Components represent physical packaging of things. Otherwise, logical components are a different level of abstraction. Classes may have attributes and operations directly. In general, components only have operations that are reachable only through their interfaces. The first difference is most important when modeling system deciding if you should use a class or a component involves if any simple decision if the thing you are modeling lives directly or a node, use a component, otherwise use a class. If the thing you modeling lives directly a node, suppose you are modeling that lives in a node, so at that time use component, otherwise use class. And second difference suggests a relationship between classes and components. Component is physical implementation set of logical elements. Component is a physical implementation of set of other logical elements such as classes and collaborations. So see this figure. This is the component with particular name as fraudagent.dll, and it have different classes with regarding these component such as fraud agent, fraud policy, pattern search. These are the different classes. Component can be shown like this figure, whereas classes can be shown like only rectangle. Okay, most of time you will never need to visualize these relationships graphically. Rather, you will keep them as a part of component specification. Sometimes you should keep like this. This is the component for agent.dll, and these are the different classes of that component. So third difference point out how interfaces bridge components and classes. As described in more detail in next PPTs, so components and classes may both realize as interface, but the component services are usually available only through their interfaces or through its interfaces. Components are also class-like in that you can specify attribute and operations for them, but this happens in rarely. components are also class-like in that you can specify attributes operations for that component, but it happens rarely. You will need to do so only if you are modeling a reflective system that can manipulate its own components. So, an interface is a collection of operations that are used to specify a service of class or component. A relationship between component and interface is important. Using one of these facilities, you decompose your physical implementation by specifying interfaces that represents a major seams in the system. You then provide components that realize the interfaces along with other components that access services through their interfaces. So components and interfaces figure shows the relationship between components and interfaces. So this there are different components. This is ionic form and this is extended form. This second form is expanded form or extended form, and part indicates first part, that is upper part of figure, indicates this ionic form. So this relationship interface you can show into two ways. First is iconic form and second is expanded form. Iconic form shows as here image observer with a circle. There is no expanded form of these image observer, only circle. Okay, so this component sends the message or first style. This is the first style renders interface with iconic form. This component realize the interface is connected to the interface using yielded realization relationships. And this is the second style. Second style renders the interface in its expanded form, perhaps revealing its operations. This is expanded form of interface. It have different operations, different attributes, whatever. So the component that realizes the interface is connected to the interface using full realization relationship. In both cases, this iconic form and expanded form. In these both cases, component that access the services of other component through the interface of connected to the interface using a dependency relationship. So there are different kinds of components, nearly about three different kinds of components may be distinguished. So first there is a deployment component. These are components necessary and sufficient to form executable system such as dynamic libraries and executables. Second, there are work product components. These components are essentially the result of development process consisting of the things such as source code files and data files from which deployment components are created. The components do not directly participate in an executable system but work product of development that used to create the executable system. The third part is the execution components. These components are created as a consequence of executing system such as com plus object which is instantiated from the dynamic libraries, that is DLL. You can also organize components by specifying dependency, generalization, association with aggregation, and realization relationships among them. So, what are the common modeling techniques or modeling executable and libraries? The most common purpose for which you will use component is to model the deployment components that make up your implementation. If you are deploying a tribal system whose implementation consists of exactly one executable file, you will not need to do any component modeling. If, on the other hand, the system you are deploying is made up of several executable and associated objects, libraries will be essential. Libraries So components modeling is even more important if you want to control the versioning and configuration management of these parts as your system evolves. So for most systems, these deployment components are drawn from the decisions you make about how to segment the physical implementation of your system. These decisions will be affected by number of technical issues based on the operating system facilities, configuration managements, that is the part of change of over time, and reuse issues, that is deciding which component you can reuse or form of from other systems. So what we studied, or what are the hints and tips regarding the components? When you model the component in UML, remember that you are modeling the physical dimensions. A well-structured component provides a crisp abstraction of something drawn from the physical aspects of system. A well-structured component provides the realization of small, well-defined set of interfaces. A well-structured component directly implements a set of classes that work together to carry out the semantics of these interfaces, which economy and elegance. A well-structured component is loosely coupled relative to other components. Most often, you will model components only in connection with dependency and realization relationships. When you draw a component in UML, use the iconic form of interface unless it is necessary to explicitly reveal the operations offered by that interface. When you draw component in UML, show only those interfaces that are necessary to understand and meaning of that component in the given context. When you draw component in UML, especially if you are using components to model things such as libraries and source code, reveal the values of tags associated with versioning. Now, now move towards next part is a deployment. In this chapter, we will study node and connections, modeling processors and devices, modeling the distribution of components, system engineering. So nodes, just like a component, live in material world and are important building blocks in modeling the physical aspects of system. A node is a physical element that exists at a runtime and represent the computational resource, generally having at least some memory and often processing capability. You use nodes to model the topology of hardware on which your system executes. Your node typically represents a processor or a device on which components may be deployed. Good nodes crisply represent the vocabulary of hardware in your solution domain. So, introduction of the deployment. The components you develop or reuse as a part of software intensive system must be deployed on some set of hardware in order to execute. This is in effect what software intensive system is all about. Such a system encompasses both software and hardware. When you architect a software intensive system, you have to consider both logical and physical dimensions. On logical side, you will find the things such as classes, interfaces, collaborations, interactions, and state machines. On the physical side, you will find the components that represent the physical packaging of the logical things, and nodes which are represent hardware on which these components are deployed and execute. So this cube, in the shape of cube, we can show the deployment or deploy the structure. So this is the graphical notation of node. This cube, in the shape of cube, we can show the node in the form of graphical notation, and this is the name of that node. This canonical notation permits to visualize a node apart from any specific hardware. So using stereotype, one of the UML extensibility mechanisms you can or often will tailor these notation to represent specific kinds of processes and devices. The UML is mainly intended for modeling software intensive system, although the UML in conjunction with textual hardware modeling language such as VHDL can be quite expressive for modeling hardware systems. The UML is also sufficiently expressive for modeling the topologies of standalone, embedded, client server and distributed system. So what are the terms and conditions regarding these node or deployment system? So a node is a physical element that exists at runtime and represents a computational resource, generally having at least some memory and often processing capability. Graphically, a node is rendered as a cube. Every node must have a name that distinguishes it from other nodes. A name is in textual string like this. It we can represent in both ways, simple name and path name. These first two figures, upper figures, are have simple name for these nodes. Some nodes have attributes in this example sales have attributes that is deploys post.exe contacts.exe sales and kiosk underscore 7 is the simple name of the node whereas extended or path name so is prefixed by the name of package. Here package name is server scope resolution and then name of node. This is path node, server scope resolution backup. This is extended node. So node is typically drawn only its name. So class with a class you may draw nodes around with tagged values or with additional components to expose their details. What are the terms and concepts regarding nodes or deployment? A node name may be text consisting of any number of letters, numbers, or certain punctuation marks, except colon or scope resolution. Except a colon, you can use punctuation mark. In practice, node name is a short noun or noun phrase drawn from vocabulary of the implementation. So nodes and components. In many ways, nodes are a lot like components. Both have names, both maybe participate in dependency, generalization, and association relationships. Both may be nested, both may have instances, both may be participants in interactions. However, they are some significant there are some significant differences between nodes and components. Components are the things that participates in execution of system. Nodes are the things that executes components. Nodes are the things that execute the components, whereas the components are the things the participation in execution of system. Components represents physical packaging of logical elements. Nodes represents physical deployment of components. These two differences. So first difference is most important. Simply put, node execute component and components are the things executable executed by the nodes. The second difference suggests the relationship among classes, components, and nodes. In particular, component is materialization of set of other logical elements. Components are deployed. A class may be implemented by one or more component and in turn a component may be deployed on one or more nodes. So this is this figure shows the relationship between nodes and components. So it deploys can be shown explicitly using dependency relationships. Most of time you won't need to visualize their relationships graphically, but will keep them as a part of nodes specification. So here, see this figure carefully. See this figure carefully. Cells have attribute parts post.exe, deploys, contacts.exe, and same figure here. These attributes, that is, these are the components post.exe and contacts.exe. These are the components of these nodes. These acts as attributes of that nodes. A set of objects or components that are allocated to a node as a group is called as distribution unit. Nodes are also class-like in that you can specify attributes and operations for them. For example, you might specify that node provide the attributes processor speed and memory as well as operations turn on, turn off and suspend. So how to organize a node? You can organize nodes by grouping them in packages in same manner in which you can organize classes and components. You can also organize nodes by specifying dependency, generalization, and association with aggregation relationships among them. So
हॅलो.
धवल धवल येते ना हो ओके see this figure carefully you can organize nodes by grouping them in packages in same manner in which you can organize classes and components. So you can also organize nodes by specifying dependency, generalization, and association with aggregation. So what are the connections between nodes? So the most common kind of relationship you will use among nodes is an association. In this context, an association represents the physical connections among nodes such as Ethernet connections, a serial line, or shared bus. You can even use association with model indirect connections such as a satellite link between different processors or distant processors. So what are the common modeling techniques or modeling processors and devices? So modeling the processors and devices that form topology of a standalone embedded client server or distributed system is most common use of nodes because all of the UML's extensibility mechanisms apply to nodes that you will often use stereotypes to specify new kinds of nodes that you can use to represent specific kinds of processors and devices. A processor is a node that has processing capability, meaning that it can execute component. A device is a node that has no processing capability, at least none that are modeled at this level of abstraction and in general represents something that interfaces to the real world. To model processors and devices, to identify computational elements of systems deployment, deployment view, and model each as a node. If these elements represent generic processors and devices, then stereotype them as such. If they are kinds of processors and devices that are part of the vocabulary of your own domain, then specify an appropriate stereotype with an icon for each. As with class modeling, consider the attributes and operations that might apply to each node. So nodes are probably the most stereotyped building blocks in UML. When, as a part of system engineering, you model the deployment view of software-intensive system, there is a great value in providing visual cues that speak to your intended audience. If you are modeling processor that is a common kind of computer, render it with an icon that looks like that a computer. If you are modeling a common device such as cellular phone, fax, modem, or camera, render it with an icon that looks like that device. So modeling the distribution of the components. When you model the topology of system, it's often useful to visualize or specify the physical distribution of its components across the processors and devices that make up the system. To model the distribution of components for each significant component in your system, allocate it to a given code. Consider duplicate locations for components. It is not uncommon for same kind of component to reside on multiple nodes simultaneously. So render this allocation one of three ways. There are three different ways you can use any one way. So first, don't make allocation visible, but leave it as a part of backplane of your model that is in each node's specification. Second, using dependency relationships. Connect each node with the components it deploys. And third, list the components deployed on a node in an additional compartment. So modeling the distribution components using this third approach, the figure shows the earlier diagram. See the previous figure carefully. This figure can be shown by using the approach. That is, the third approach is a list components deployed a node in additional compartment. This is the figure that is modeling the distribution of the components. So this diagram is a bit differ from previous one. In that object diagram, visualizing specific instances of each node. In this case, or rare form, the queues instances. This is the queues and instances are both anonymous, and the other two instances named C. This is second instance console. C for console and S for server. These two instances. So each processor in this figure rendered with additional compartment showing the component deploys. You see in this console figure, console deploys admin.exe and configuration.exe. Similarly, server deploys database admin.exe and other file. So what we learn, or what are hints and tips? A well structured document or a well structured node provides a crisp abstraction of something drawn from the vocabulary of the hardware in the solution domain. A well structured node is decomposed only to the level necessary to communicate your intent to the reader. A well structured node exposes only those attributes and operations that are relevant to the domain you are modeling. A well-structured node directly deploys a set of components that reside to the node. A well-structured node is connected with other nodes in a manner that reflects the topology of the real-world system. So when you draw a node in UML for a project or organization as a whole, define a set of stereotypes with appropriate icons and provide meaningful visual cues for your readers. When you draw a node in UML, show only attributes and operations, whatever, that are necessary to understand the meaning of that node in the given context. So we have completed second part. Third part is collaboration. So in this chapter, we will study collaborations, realizations, interactions, modeling the realization of a use case, modeling the realization of an operation, modeling a mechanism, refining interactions. In the context of the system architecture, a collaboration allows you to name a conceptual chunk that encompasses both static and dynamic aspects. A collaboration names a society of classes, interfaces, and other elements that work together to provide some cooperative behavior that's bigger than the sum of all its parts. You use collaborations to specify the realization of use cases and operations and to model the architecturally significant mechanisms of your system. So, what is the introduction of these collaborations? In UML, you model mechanism using collaborations, or collaboration gives a name to the conceptual building blocks of your system, encompassing both structural and behavioral elements. For example, you might have a distributed management information system whose databases are spread across several nodes. From the user's perspective, updating information looks automatic. From the inside perspective, it is not so simple. From outside perspective or user's view, updating information looks like automatic, but inside view it is not simple because such an action has to touch multiple machines. To give the illusion of simplicity, you have you would want or you should want to devise a transaction mechanism with which a client could name what looks like a single atomic transaction even across various databases. Such a mechanism would span multiple classes working together to carry out transaction. Many of these classes would be evolved in other mechanisms as well, such as mechanisms for making information persistent. These collection of classes together with their interactions. So collection of classes, that is structural part, interaction is behavioral part. And these forms the mechanisms with which in UML you can represent as a collaborations. So collaboration diagrams can be shown such as elliptical shape, dotted elliptical shape. So it have particular name, that is this elliptical shape, that is this collaboration have name internode messaging. So collaborations not only name as systems mechanisms, they also serves as a realization of use cases and operations. The UML provides a graphical representation of collaborations in the form of elliptical shapes. This notation permits you to visualize structural and behavioral building blocks of system, especially as they may overlap the classes, interfaces, and other elements of the system. This notation lets you to visualize a collaboration from the outside as one chunk. What's often more interesting is what's inside in this notation. Zoom into the collaboration and you will lead other diagrams, most notably class diagrams for collaboration structural part and interaction diagrams for collaboration behavioral part. So how naming can be given to the this collaboration? So every collaboration must have name that distinguishes it from other collaborations. A name is in textual string, that name alone known as a simple name. A path name is in collaboration is prefixed with name of package in which that collaborations lives. A collaboration name may be text consisting of any number of letters, numbers, and certain punctuation marks except colon and may continue several lines. In practice, collaboration names are short nouns or noun phrases done from the vocabulary of you system you are modeling. Typically, you capitalize the first letter of the collaboration. See here, first letter of this collaboration is capital. So transaction or chain of responsibility. So what is the behavior part of the collaboration? The structural part of collaboration is typically rendered with class diagram, and behavioral part of collaboration typically rendered with interaction diagram. So an interaction diagram specifies the interaction that specifies the behavior comprised of set of messages that are exchanged among a set of objects within the context to accomplish a specific purpose. An interaction context is provided by its including collaboration, which establishes the classes, interfaces, components, nodes, and other structural elements whose instances may participate in that interaction. The behavioral part of this collaboration may be specified with one or more interaction diagrams. If you want to emphasize the time ordering messages, use a sequence diagram. If you want to emphasize the structural relationship among these objects, then as they collaborate, use collaboration diagram. Either the diagram is appropriate because for most purposes they are semantically equivalent. So see, this is the behavioral aspect of collaboration diagram. So that is when you model the society of classes. This is the society of classes by naming their interaction with collaboration. You can zoom inside the collaboration to expose the details of their behavior. So in zooming inside the collaboration named internode, messaging might be revealed the interaction diagram. So this is the actor, this is the one object, then second object message, third object outgoing queue, and fourth message is transport agents. So see this figure carefully. See this transport agent periodically remove messages from their its message from their queue according to scheduling policies. So the behavior part of collaboration must be consistent with structural part. This means that is the object found in collaborations interactions must be instances of classes found in its structural part. Similarly, the messages named in an interaction must relate to the operations visible collaborations structural part. You can have more than one interactions associated with collaborations, each of which may show a different but consistent aspect of its behavior. So what are the common modeling techniques? So one of the purpose for which you will use collaboration is to model the realization of use case. You will typically drive the analysis of your system by identifying your system's use case, but when you finally turn to implementation, you will need to realize these use cases with concrete structure and behaviors. In general, Every use case should be realized by one or more collaborations for the systems as a whole. The classifiers involved in a given collaborations that is linked to a use case will participate in other collaborations. So in this way, the structural contents of collaborations tend to overlap one another, and to model the realization of the use case, to identify those structural elements necessary and sufficient to carry out these semantics of use case, capture the organization of these structural elements in the class diagrams, consider the individual scenarios that represents this use case. Each scenario represents specific paths through the use case. Capture the dynamics of these scenarios in interaction diagrams. Use case use sequence diagrams if you want to emphasize the time ordering of the messages. Use collaboration diagrams if you want to emphasize the structural relationships among those objects as they collaborate. Organize these structural and behavioral elements as a collaboration that they can connect to use case via realization. So to model the implementation of an operation, identify parameters, return values, and other objects visible to the operation. If the operation is a trivial, represent implementation directly in code, which you can keep the backplane of your model and or explicitly visualize it in a note. If the operation is algorithmically intensive, model its realization using activity diagram. If the operation is a complex or otherwise requires some detailed design work, represent its implementation as a collaboration. You can further expand the structural and behavioral part of this collaboration using class and interaction diagram respectively. So to model a mechanism, identify the major mechanisms that shape your system's architecture. These mechanisms are driven by overall architectural style you select to impose on your implementation, along with the style of appropriate problem domain. Represent each of these mechanisms as collaboration. Expand on structural and behavioral part of each collaboration. Look for a sharing where possible. Validate these mechanisms early in the development lifecycle, but involve them with each new realize as you learn more about the details of your implementation. So, what we studied, or what are the hints and tips regarding the collaboration diagrams? When you model collaboration in UML, remember that every collaboration should represent either realization of use case or operation, or should stand alone as a mechanism of a system. So a well-structured collaboration consists of both structural and behavioral aspects. A well-structured collaboration provides a crisp abstraction of some identifiable interactions in the system. A well-structured collaboration is rarely completely independent, but will overlap with the structural elements of other collaborations. A well-structured collaboration is understandable and simple. So when you draw a collaboration in UML, explicitly render a collaboration only when it is necessary to understand its relationships to other collaborations, classifiers, operations, or the systems as a whole. Otherwise, use collaborations but keep them in backplane. When you draw a collaborations in UML, organize collaborations according to the classifiers or operations they represent or in package associated with the system as a whole. So we have completed collaboration. Next part is patterns and frameworks. So in this part, we will study patterns and frameworks, modeling the design patterns, modeling the architectural patterns, making patterns approachable. So a well-structured system are full of patterns. A pattern provides a common solution to common problem in a given context. A mechanism is a design pattern that applies to a society of classes. A framework is typically architectural pattern and that provides an extensible template for applications within a domain. You use patterns to specify mechanisms and frameworks that shape the architectures of the system. You make a pattern approachable by clearly identifying slots, tabs, knobs, and dials that a user of that pattern may adjust in order to apply the pattern in particular context. So introduction of this pattern, this figure shows mechanisms and frameworks. So in UML, you will typically model design patterns called as mechanisms. Patterns also known as mechanisms, which you can represent in the form of collaborations. These elliptical shapes known as patterns or mechanisms it have a particular name. Similarly, you typically model architectural patterns as a framework. This is architectural pattern can be shown in the form of rectangle and it have a particular name. So and framework you can represent stereotyped package. See in this figure, this is angle brackets for framework and then framework name is written. So UML provides graphical represents for both kinds of patterns. So what is pattern and architecture? Patterns are the part of UML simply because patterns are important parts of developers vocabulary. By making the patterns in your system explicit, you make your system far more understandable and easier to evolve and maintain. Patterns help to visualize, specify, construct, and document their artifacts as a software intensive system. You can forward engineer a system by selecting an appropriate set of patterns by applying them to abstractions specific to your domain. You can also reverse engineer a system by discovering the patterns it embodies, although that's hardly a perfect process. Even better, when you deliver a system, you can specify the patterns it embodies so that when someone later tries to reuse or adapts that system, its patterns will be clearly manifest. In practice, there are two types of patterns that is interest design patterns and framework. The UML provides meaning of modeling both. When you model either pattern, you will find that it typically stands for the larger packages except for dependency relationship bind them to other parts of your system. So in UML, you model a framework as a stereotyped package. Zoom inside the package, you will see mechanisms that live in any various views of the system's architecture. For example, not only might you find parameterized collaborations, you might also find use cases as well as plain collaborations. So frameworks can be distinguished from the plain classes libraries. A class library contains abstractions that your abstractions instantiate or invoke. A framework contains abstractions that may instantiate or invoke the abstractions. Both of these kinds of connections constitute the framework slot, tab, knob, or dials that you must adjust in order to adapt the framework to your context. See the figure of framework. So figure shows the framework named as cyclic executive. This framework name is cyclic executive. Okay, encompassing a set of event classes only with the mechanism event handler and common events. So event handler for the processing these events in cyclic fashion. A client that builds on these frameworks such as pacemaker, the client handler with pacemaker could blind on abstractions in common events via subclassing and could also apply instance of event handler mechanism. See the figure carefully. So what are the common modeling techniques? What are the common modeling techniques? One thing you for which you will use patterns to model a design pattern. When you model mechanisms such as these, you have to take into account its inside as well as outside view. When viewed from outside, a design pattern rendered as a parameterized collaboration. As a collaboration, a pattern provides a set of abstractions whose structure and behavior work together carry out some useful functions. And the collaborations patterns name the element that a user of this pattern must bind. And this makes the design pattern a template that you use a particular context by supplying the elements that match the template parameters. When viewed from the inside, a design pattern is simply a collaboration and is rendered with its structural and behavioral parts. Typically, you will model the inside the collaboration with the set of class diagrams for structural aspects and set of interactions for behavioral aspects. The collaboration parameters name certain of these structural elements which, when the design pattern is bound in a particular context, are instantiated using abstractions from the context. To model a design pattern, identify common solutions to common problem and refine it as a mechanism. Model the mechanism as a collaboration, providing structural as well as its behavioral aspects. Identify the elements of design pattern that must be bound to a element in a specific context and render them as a parameter to the collaboration. So, what is modeling architectural patterns? The other thing for which you will use pattern to model architectural patterns. When you model such framework, you are in effect modeling infrastructure of an entire architecture that you plan to reuse and adapt to some context. A framework is rendered as stereotyped package. As a package, a framework provides set of elements including but certainly not limited to classes, interfaces, use cases, components, nodes, collaborations, and even other frameworks. In fact, you will place in framework all the abstractions that work together to provide an extensible template for applications within a domain. Some of these elements will be public and represent resources that client can build on. These are the types of the framework that you can connect to the abstractions in your context. Some of these public elements will be design patterns and represent resources to which client bind. These are the slots of the frameworks that you fill when you bind these design patterns. Some of Finally, some of these elements will be protected or private to represent encapsulated elements to the framework that are hidden from the outside view. When you model an architectural pattern, remember that framework is in fact a description of an architecture, albeit one of is incomplete, possibly parameterized. As such, everything you know about modeling a well-structured architecture applies to the modeling a well-structured framework. The best frameworks are not designed in the isolation. To do so is an guaranteed way to fail. Rather, the best frameworks are harvested from the existing architectures that are proven to work, and the frameworks evolve to find slots, tabs, knobs, and dials that are necessary and sufficient to make that framework adaptable and other domains. So, to model and architecture patterns, harvest frameworks from existing and proven architecture. The model the frameworks as stereotyped package containing all the elements, especially the design patterns that are necessary and sufficient to describe the various views of the framework. So expose the slots, tabs, knobs, dials necessary, adapt the framework in the form of design patterns and collaborations. For most part of these means making it clear to user of the pattern which classes must extended, which operations must be implemented, and which signals must be handled. So, what we learn, or what are the hints and tips regarding patterns and frameworks? So, When you model pattern in UML, remember that they work at many levels of abstractions from individual classes to the shape of the system as a whole. The most interesting kinds of patterns are mechanisms and frameworks. A well-structured pattern solves common problem in common way. A well-structured pattern consists of both structural and behavioral aspects. A well-structured pattern is automatic, meaning that it is not easily broken into smaller patterns. A well structured pattern tends to cut across individual abstractions in the system. When you draw a pattern in UML, expose the elements of pattern that you must adopt to apply it in the context. When you draw a pattern in UML, make the pattern approachable by supplying use cases for using as well as adopting the pattern. So we have completed pattern and framework. Next part is component diagram. So in this chapter, we will study modeling source code, modeling executable realizes, modeling physical databases, modeling adaptable systems, forward and reverse engineering. So components are one of the two kinds of diagram found in modeling the physical aspects of object oriented system. A component diagram shows the organization of dependencies among the set of components. You use component diagrams to model the static implementation view of system. This involves modeling the physical things that reside on a node, such as executable libraries, tables, files, and documents. Component diagrams are essentially class diagrams that focus on systems component. Component diagrams are not only important for visualizing, specifying, and documenting components based system but also for constructing executable systems through forward and reverse engineering. So this figure shows the component diagram. So with UML component diagram visual static based aspects of physical components and their relationships. These are the pages. These are the pages related. These are the pages. These are the library files, and this is the component. So all these are known as the components. So what are the terms and concepts of components? A component diagram shows the set of components and their relationships. Graphically, a component diagram is collection of vertices and arcs. So component diagram is just a special kind of diagram that shares same common properties as do all other diagrams, a name and graphical contents that are projection into a model. What distinguishes a component diagram from all other kinds of diagram is its particular content. So what are the contents? That is components and interfaces, dependency, generalization, association, and realization relationships. Like other diagrams, component diagrams may contain nodes and constraints. Component diagrams may also contain packages or subsystems, both of which are used to group elements of these models into longer chunks. Sometimes you will want to place instances in your component diagrams as well, especially when you want to visualize one instance of family of component based system. So in many ways a component diagram is just like a special kind of class that focuses on systems components. So, what are the common uses of component diagrams? So, these are the common uses to model source data, to model executable realize, to model physical database, and to model adaptable systems. We will learn in detail. So to model source code with most contemporary object oriented programming languages, you will cut code into integrated development environments to store the source code in your file. You can use this component diagram to model configuration management of these files, which represents work product components. Then to model executable re- releases. So a release is relatively complete and consistent set of artifacts delivered to internal or executable user. In the context of component, a release focuses on the part of necessary deliver a running system. When you model release using component diagram, you are visualizing, specifying, or documenting the decisions about the physical parts of the constitute of your software, that is its deployment component. Then third is model physical database. Think of physical database as concrete realization of schema living in the world of bits. Schemas in effect offer an API to persistent information. The model of physical database represents the storage of that information in the tables of relative databases or the pages of an object-oriented databases. You use common diagrams so to represent these and other kinds of physical databases. Then fourth is model adaptable systems. Some of systems are quite static. Their components enter in scenes, participate in an execution, and then depart. Other systems are more dynamic, involving mobile agents or components that migrate for the purpose of load balancing and failure recovery. You can use component diagrams in conjunction with some of the UML's diagrams for modeling behavior to represent these kinds of systems. So to model a system's source code either by forward or reverse engineering, identify the set of source code files of interest and model them as components stereotyped as files. For larger systems, use packages to show group of the source code files. So consider exposing a tagged value indicating with information as a version number of the system code files, its author, and the the date it was last changed. Use tools manage the value of this tag. Model the compilation dependencies among these files using dependencies. Again, use tools to help generate and manage these dependencies. To model executable realizes to identify set of components you should like to model. Typically, this will involve some or all the components that live on one node or distribution of these sets of components across the nodes in the system. Consider the stereotype of each component in this set. For most systems, you will find two smaller number of different kinds of components. You can use UML's extensibility mechanism to provide visual cues for these stereotypes. For each component in this set, consider the relationship to its neighbors. Most often, this will involve interfaces that are exported by certain components and then imported by others. So, if you want to expose the seams in your system, model these interfaces explicitly. If you want to model at a higher level abstraction, elide these relationships by showing only dependencies among the components. So modeling, this is modeling physical database. So a logical database schema captures the vocabulary of systems persistence data with semantics and their relationships. So physically things are stored in database for lateral retrieval, either a relational database, an object oriented one, and hybrid object oriented database. So the UML is well suited for modeling physical database as well as logical database schema. So physical database design is beyond the scope of this syllabus. So focus here is simply to show how to you can model database and tables using the UML. Mapping the logical database schema to an object-oriented databases is straightforward because even complex inheritances latencies you can made persistent directly. Mapping a logical database schema to relational database is not a simple. However, in persistence of inheritance, you can make decisions about how to map classes and tables. Typically, you can apply one or combination of these three strategies, such as define separate table for each class. This is simple but naive approach because it introduces maintenance headaches when you add new child classes or modify your parent classes. Second, collapse your inheritance latency. If every class in a hierarchy has same state, the downside with the approach that you end up sorting superflows information for many instances. And third, separate parent and child state in different tables. This approach is best mirrors your inheritance lattice, but downside is traversing your data will require many cross tables joins. So modeling a physical database, when you designing physical database, you will have to make decisions about how to map operations defined in your logical database schema. So object-oriented database makes mapping fairly transparent, but with relationships, you have to make some decisions about how these logical operations are implemented. So again, you have some choices. First, use simple CRUD, that is create, read, update, and delete. That is CRUD operations. Implement them with standard SQL or more or stored procedures. So given these general guidelines to model physical database, identify the classes in your model to represent your logical database schema. Select a strategy for mapping these classes. The tables, you will also want to consider the physical distribution of your database. Your mapping strategy will be affected by the location in which you want to your data to live in your deployed system. To visualize, specify, construct, and document your mapping, create a component diagram that contain components stereotyped as tables. Where possible, use tools help you transform logical design into physical design. So, forward and reverse engineering. Forward engineering and reverse engineering components are pretty direct because components are themselves physical things, such as libraries, tables, files, documents, are therefore close to running system. When you forward engineer a class or collaboration, really forward engineer to a component that represents a source code binary library, or executable for a class or collaboration. Similarly, when you reverse engineer source code, binary libraries or executable, you really reverse the engineer to a component or set of components that in turn trace to classes or collaborations. So to forward engineer component diagram, for each component, identify classes or collaborations that the component diagrams implement. Select the target for each component or binary library or executable file. Then select use tools for forward engineer your models. So forward engineer for each component, identify the class or collaboration that component implements. Select target for each component. Your choice is basically between source code or binary library or executable file. Use tools for forward engineer your model. Then reverse engineer component design. Select the target you want to reverse engineer. Source code can be reverse engineered to components and then classes. Binary libraries can be reverse engineered but uncover their interfaces. Executables can be reverse engineered the list. Using tool, point to the code you should like to reverse engineer. Use your tools to generate a new model to notify an existing one that was previously forward engineered. Using your tool, create component diagram for querying this model. For example, you might start with one or more components, then expand the diagram by following relationships and neighboring components. Expose or hide the details of components of this component diagram as necessary to continue your intent. So, what are the hints and tips regarding these component diagrams? So when you create component diagram in UML, remember that every component diagram is just a graphical representation of static implementation view of system. That is, no single component diagram need capture anything about systems implementation view. Collectively, all component diagrams of system represent the system's complete static implementation view. Individually, each represents just one aspect. So, a well-structured component diagram is focused on communicating one aspect of system's static implementation view. A well-structured component diagram contains only those elements that are essential to understanding that aspects. A well-structured component diagram provides details consistent with its level of abstractions, with only those adornments that are essential to understanding exposed. A well-structured component diagram is not so minimalist that is misinformed to the reader about the important semantics. When you draw component diagram, give it a name that communicate its purpose. Lay out its elements to minimize lines that cross. Organize its element specially so that things that are semantically close laid out physically close. Use notes and colors and visualize cues to draw attention and to important features of your diagram. Use stereotyped elements carefully. Select a small set of common icons for your projects or organizations and use them consistently. Last part last part from this chapter is deployment diagrams, and this is also last part from your syllabus. So in this chapter we will study modeling an embedded system, modeling a client server system, modeling a fully distributed system, forward and reverse engineering. So deployment diagrams are one of the two kinds of diagrams used in modeling the physical aspects of object-oriented system. A deployment diagram shows the configuration of runtime processing nodes and the components that live on both live on them. You use deployment diagrams to model static development of your system. For the most of part, this involves modeling the topology of hardware on which your system executes. Deployment diagrams are essentially class diagram that focuses on systems nodes. Deployment diagrams are not only important for visualizing, specifying, and documenting embedded client server and distributed system but also for managing executable systems through forward and reverse engineering. So when you create software intensive system your main focus as a software developer is an architecturing and deploying its software. However, as system engineer, your main focus is on systems, hardware, and software, and in managing the trade-offs between the two. Whereas the software developer works with somewhat intangible artifacts such as models and codes. System developers work with quite tangible hardware as well. So the UML is primarily focused on the facilities for visualizing, specifying, constructing, and documenting software artifacts, but it is also designed to address hardware artifacts. So in UML, you use class diagrams and component diagrams to reason about the structure of your software. You use sequence diagrams, collaboration diagrams, state chart diagrams and activity diagrams to specify the behavior of system. At the edge of your system software and hardware, you use deployment diagram to reason about topology of processors and devices on which your software executes. So this is the example of deployment diagram. So with UML, you use deployment diagram to visualize a static aspect of these physical nodes and their relationships to specify the detailed constructions. See the figure carefully of deployment diagram. What are the terms and concepts of deployment diagram? The deployment diagram is a diagram that shows the configuration of a runtime processing nodes and the components that lie on them. Graphically, a deployment diagram is collection of vertices and arcs. So a deployment diagram is just a special kind of diagram that shares same common properties as all other diagrams such as name, graphical contents that are the projection into the model. So they distinguish a deployment diagram from all other kinds of diagram is particular content. So deployment diagrams commonly contain nodes, dependency and associations relationships. Like other diagrams, deployment diagram may contain nodes and constraints. Deployment diagrams may also contain components, each of which must live on some node. Deployment diagrams may also contain packages or subsystems, both of which are used to group elements of your model into target chunks. Sometimes you will want to place instances in your deployment diagrams as well, especially when you want to visualize one instance of a family of hardware topology. So what are the common uses of deployment diagram? So when you use deployment diagram to model static deployment view of the system. This view primarily addresses the distribution, delivery and installation of the parts that make up the physical system. There are some kinds of systems for which deployment diagrams are unnecessary. If you are deploying the piece of software that live on one machine and interface only with standard devices on that machine are already managed by a host operating system, and you can ignore the deployment diagrams. On the other hand, if you are developing a piece of software that interacts with devices and devices that host the operating system does not typically manage, or that is physically distributed across multiple processors, then using deployment diagrams will help you reason about your system's software to hardware mapping. So there are three common uses: to model embedded system, to model client server system, to model fully distributed system. So we will see one by one. So to model embedded system, an embedded system is software intensive collection of hardware that interface with physical world. Embedded system involves software that controls devices such as motors, actuators and display, and that in turn is controlled by external stimuli such as sensor input, movement, and temperature changes. You can use deployment diagrams to model devices and processors that comprise an embedded system. So, second, to model client server system, a client server system is a common architecture focuses on making a clear separation of concerns between the system's user interface. Client server system are one end of continuum of distributed system and require you to make decisions about network connectivity of clients to servers and about the physical distribution of your system's software components across the nodes. You can model the topologies such as systems by using deployment diagrams. Third, to model fully distributed system, at the other end of continuum of distributed system are those that are widely, if not globally distributed, typically encompassing multiple levels of servers. Such systems are often hosted to multiple versions of software components, some of which may even migrate from node to node. Crafting such systems requires you to make decisions that enable the continuous changes in systems topology. You can use deployment diagrams to visualize the system's current topology and distribution of components to reason about the impact of changes on that topology. So to model an embedded system, identify the devices that are unique to your system. Provide visual cues, especially for unusual devices, by using UML's extensibility mechanisms to define systems specific stereotypes with the appropriate icons. At very least, you will want to distinguish processors and devices at the level of abstraction. So model the relationship among these processors and devices in a development diagram. Similarly, specify the relationship between the components in your system's implementation views and the model in your system's deployment view. As necessary, expand on an intelligent device by modeling their structure with more detailed deployment diagram. So to model client server system, identify the nodes and represent systems client server processor, highlights those devices that are German the behavior of your system. For example, you want to model special devices such as credit card readers, budget readers, and display devices other than monitors because their placement in systems hardware topology are likely to be architecturally significant. Provide visual cues for these processors and devices via stereotyping. Model the topology of these nodes in a deployment diagram. Similarly, specify the relationship between the components in your system's implementation view and nodes in your system's deployment view. And for example, see in this figure is modeling the client server system. This is whole rectangle indicates the server. So catching server and processing server. So deploys different operations, and these are the clients such as kiosk, consoles. These are the clients. So client package contains two nodes, both of which stereotyped and visually distinguishable, whereas server packages contains two kinds of nodes and both have been adorned with some components to in each. So to model a fully distributed system, identify systems, devices and processors are simpler to the server client server system. If you need to reason about the performance of systems network or the impact of changes to the network, be sure to model these communication devices to the level of details sufficient to make these assessments. Pay close attention to logical grouping of nodes, which you can specify by using packages. Model these devices and processors using deployment diagrams. Where possible, use tools that discover the topology of your system by walking your system's network. If you need to focus on the dynamics of your system, introduce use case diagram to specify these kinds of behavior you are interested in expand these use cases on interaction diagrams. So this is modeling fully distributed deployment diagram. These are the different consoles connected with internet, and these are the different servers connected with internet. So you can here in this figure there are three consoles linked by internet and three instances of regional servers. These are the three regional servers connected with internet at front ends and country servers, which is one of one with logging server. So forward engineering and reverse engineering, there is only a modest amount of forward engineering that you can do with deployment diagram. For example, after specifying the physical distribution of components across the nodes of the deployment diagram, it is possible to use tools that then push these components out to the real world. For system administrators, using the UML in this way helps you to visualize these what can be a very complicated task. Reverse engineering from the real world back to the deployment diagram is of tremendous value, especially for fully distributed systems that are under constant change. You will, you will want to supply set of stereotyped nodes that speak to the language of your system's network administrators in order to tailor the UML to their domain. The advantage of using UML is that it offers a standard language that addresses not only their needs but the needs of your project software developers as well. So to reverse engineering in deployment diagram, select the target that you want to reverse engineer. In some cases, you will want to sweep across the entire network. In other, you can limit your search. Select also the fidelity of the reverse engineering. In some cases, it is sufficient to reverse engineer just to the level of an system's processes. In others, you will want to reverse engineer to the system's networking peripherals as well. Use the tools that works across your system, discovering its hardware topology. Record that topology in a deployment diagram. Along the way, you can use similar tools to discover the components that live on each node, which you can also record in deployment model. You will want to use intelligent search for even basic personal computer can contain gigabytes of components, many of which may not be relevant of your system. Then hints and tips. So when you create deployment diagrams in UML, remember that every deployment diagram is just a graphical representation of static deployment view of system. That is, no single deployment diagram need capture everything about system's deployment view. Collectively, all the deployment diagrams of the system represent the system's complete static deployment view. Individually, each represents just one aspect. So, a well-structured deployment diagram focuses on communicating one aspect of system's static development view. It contains only those elements that are essential to understand that aspects. It provides details consistent with its level of abstraction, expose only those adornments that are essential to understand. It is not to minimalist and misinform the reader about the importance semantics. When you draw a deployment diagram, give a name that communicate its purpose, give layout its element to minimize lines across, organize its elements spatially so that the things that are semantically close laid out the physically close. Use nodes and colors and as visual cues and draw attention to important features of your diagram. Use stereotyped semantics carefully. Select a small set of the element icons for your project or organization and use them consistently. So this is the end of the chapter.